I'm going to show you how to make your queries more than 43,000 times faster using indexes. If that sounds scary, you're probably in the right place, plus it's not actually scary at all. It's like one SQL statement. We're going to go through what an index is, how to create one, and most importantly, how to benchmark and measure the performance of your queries to ensure that index is working the way you expect. Indexing is one of those fundamental skills that you need to understand when working with databases. And I don't mean managing databases like a DBA. Indexes are one of the best tools that developers have to greatly reduce the amount of time it takes your application to fetch data. So let's get into it. Here we have a people table with just over 1 million rows. Let's say we want to write a simple query that finds my user based on their username. Let's head over to the SQL editor, which is where we can write raw SQL to query our Postgres database hosted by Supabase. But this could be any Postgres database. It could be running locally on your machine or hosted anywhere on the internet. And let's create a new query where we're going to select all of the columns from the people table where the username column is equal to the string Jon. And if we run this query, we can see it's taking a very long time. Imagine if it took this long just to get results from typing into a search box in your application. You know, something other than Jira. Anyway, this is unusable, and we can measure exactly how unusable by adding the words explain and analyze before our query. And if we run this one, we can see the query plan that Postgres used to perform this query as fast as possible. And so it took 17,011 milliseconds to complete, or about 17 seconds that the user would have been waiting for those results. Now, with the magic of editing, this looks like it just gave us a number immediately, but it did actually take 17 seconds to run. And this is because explain analyze actually runs the query and measures how long it takes. Just a heads up in case you try to use it on, say, a delete query on the production database. I swear I've never made that mistake before. But 17 seconds is too long to wait to look up a single user, and the reason this took so long was because this performed a sequential scan on the people table. Now, databases are incredibly fast at doing that, hence why it only took 17 seconds to ask that question about 10 million times, but we can greatly reduce this using an index. And they're dead simple, at least to begin with. So let's create a new query and use this to create an index on the people table using the username column. And if we run that, it's going to take a while because it's essentially creating a whole new, much faster copy of that username column that Postgres can use to look up those values very quickly. And once that says success, no rows returned, that means it's finished. So we can go back over to our select statement that's looking for that Jon user. Remember that last time that took 17,000 milliseconds. Let's try and run that again with our indexed username column, and we can see the execution time has plummeted down to 3 milliseconds. So an index stores a copy of the column, in this case username, and then a pointer back to the full row in the people table so it can go and look up the other columns. So to perform this query, Postgres did an index scan using that index we created on the username column, which exists on the people table. So the username index was used to find this Jon value, but then because we were selecting all of the columns in that table, the index's pointer was used to look up that full row in the people table, which means Postgres was able to avoid doing a full sequential scan of the people table just to get those extra columns of data. It knows how to jump to the exact row or rows in the people table because it has that pointer. And something interesting to note is it will only go off to the original table if it needs that additional data. So since our index stores a copy of the username, if we were to only select the username column and run this query with explain analyze, we'll see it performed an index only scan, meaning the index was able to satisfy this entire query without going back to the people table, which is even faster. But we're probably getting a little bit ahead of ourselves. We'll be going over covering indexes, which is what that is, multi-column indexes, partial indexes, and a whole bunch more in future videos. So make sure you check out the playlist at the end of this video to become an Indexing and Postgres Pro. But even if we select all of the columns, so we're going back to that people table, and let's select a username that has thousands of people, like John with an H, and now if we run this, we can see this only took a second, and if we extend this one out, we can see we got back 3,307 rows for people that have that username. So even looking up those columns for over 3,000 people only took a second. And we've been able to accomplish that with a single SQL statement, adding an index for the username column. And Postgres will even automatically keep this up to date whenever a new row is added to the people table. It's just too easy. Postgres is also super clever about choosing whether or not to use an index. So if we create a new query and create a new table for posts with an ID that will auto increment, a title that is text, and then whether or not it is published yet, and we'll just get rid of this trailing comma because Postgres doesn't like that. Now, if we run this query, we have a post table. So let's insert 3 posts. So first post, second post, third post, and only the first 2 have been published. So if we highlight over just this statement, we can run it independently of this create table. So let's insert that data. And now we can select star or all the columns from the post table. And if we run this one, we'll see it very quickly gave us those 3 rows. And if we whack on and explain analyze and then run this query again, we'll see it used a sequential scan, but the execution time was a fraction of a millisecond. But let's see if we can improve this even further with an index. So let's create a new index on the post table and let's index the is_published column so we can quickly select all of our published posts. So let's run that to create the index, and I need to be able to spell published correctly. And then we can run this one again, and we see success, no rows returned. So let's modify our select statement to select all of the columns from posts, but only where the is_published column is equal to true. Now I wonder how much faster we've managed to make this query using that index. Let's run this select to find out, and we'll see it's still incredibly fast, but it actually performed a sequential scan on the post table. But wait, isn't that the bad one? Well, not exactly. The Postgres query planner, or the thing that decides the fastest way to perform that query, is incredibly smart. It's worked out that to use this index, it can find the isPublished column incredibly quickly, but then it still needs to use that pointer back to the original post table to get the ID and title columns, and that lookup is actually going to take longer than just doing a sequential scan over our 3 posts, but already having access to the ID, title, and isPublished columns. So indexes get exponentially more beneficial as the size of the database grows. So once we're in the hundreds of thousands, and definitely once we get to the millions of rows in a table, we probably want to consider indexing columns that are frequently used by our application. But what if our application is querying multiple columns? One has an index and the other does not. Do we need to worry about the order of our where statement in order to make the most of that index? Well, let's go back to our people table that has enough rows to use that index. And let's say we want all of the columns from the people table who are currently active. So where the is_active column is set to true. And if we run this, we can see that it's taking an incredibly long time. And with the magic of editing, we can see that it took 17 seconds and performed a sequential scan, which should be expected because we don't have an index on the is_active column. But if we were to look for our Jon user, so where username is equal to Jon, and also where their account is active, when we run this query, we can see it was lightning fast at 3 milliseconds because it could perform an index scan using our username index. Postgres knows that the username index is going to be way faster for finding that Jon user than performing a full sequential scan. So it uses the index. It finds that single user, which means it's instantly been able to throw away like 10 million records. And then it can just perform that check for the isActive column on the remaining result set of one person. But what happens if we reverse the order of this where clause? So we first select all of the people where isActive is true, and then we filter that down to just the one where the username is equal to Jon. So what do you think will happen? Well, before we run that query, let's quickly count all of the people where the is_active column is equal to true. So this will take a little while to run because we don't have that index, but once that's finished, we can see there are a bit over 1 million rows that are currently active. So about 10% of the people table. So the first part of this where clause will throw away about 90% of the table, and then we just need to find this Jon user in the remaining million or so records. But that's not what happens because, as I mentioned before, the Postgres query planner is incredibly clever. So if we run this select to get all of the active users where the username is Jon, we'll see the execution time was incredibly fast because it used our index on the username column first, knowing that this will throw away a much larger set of results, really one row short of 100%. So it uses the index and performs this part of the where clause first, and again, only has a single user that it then needs to check the isActive column. And this is also true for situations where multiple indexes are available. The Postgres query planner will look at how many rows could be eliminated with each of those indexes and chooses the most performant one. And we can test this one out by creating a new index on the people table for the first underscore name. And this one will take a little while to run. And once that's finished, we also want an index on the is underscore active column. And this will also take a while to create. And now we can test which index would be most efficient by counting the distinct values on the is underscore active column, which hopefully we can guess given it's a Boolean column, and we can see that count is 2. So we have the value true or false. But on our other indexed column of first underscore name, we can expect there'll be a few more distinct values. And we do with just over 3,000 unique first names. So if we're looking for a single value for each of these columns, so let's say a first name of Mary and the is underscore active column set to false, by choosing one first name, we're potentially going to eliminate 1/3000th of the entire table. Whereas if we're looking for a specific Boolean value, we may only eliminate half. So using the first name column is going to eliminate a greater number of rows from that result set. Therefore, the query should use the first name index over the isActive index. And we can prove this out by looking for an active user where the first name column is equal to Yvonne. And if we run this query with explain analyze, we can see the query plan chose to index scan the first name index because it was more likely to throw away the largest number of results, making the check for is underscore active happen on a much smaller data set. So indexes help to greatly reduce the amount of time it takes to query your database, especially as it grows. They're super simple to set up, and then Postgres will automatically choose the most performant path for your queries and even keeps them up to date as the data in the database changes. So why not just index every column? Well, indexes take up space. It's essentially a duplicate of the data that you want to index. It also adds a little bit of overhead to every insert, update, or delete statement on that table, as the index will also need to be updated with those changes. Someone famous probably said you should have as many indexes as you need, but as few as you can get away with. So don't be scared of creating indexes, but they aren't free, and they're not something you just set and forget. It's an ongoing process of identifying slow queries, defining an index to cover them the best you can, and then making sure those queries are actually using them. Sometimes this means tweaking the query, but maybe you just need to store a little bit of extra data in your index. But for that, you need to check out this video right here. We look at covering indexes that can satisfy an entire query without needing to go back to the original table for extra data. If you want to go deeper on Postgres generally, then I recommend you check out this playlist. We cover everything you need to know as a developer to get the most out of your database. But until next time, keep building cool stuff.